When you look at something, light from whatever you're looking at enters your eye and is focused by a lens that lies suspended on the ciliary muscle just behind the cornea. As your object of attention changes, your eye refocuses by tightening or relaxing the muscles that surround the lens, changing its curvature and so its focal length. A most unusual lens. But when you take a photograph, you're essentially doing the same thing. Light is focused by a lens system onto the plane of the film, where the image is recorded. Inside a cheap camera, you'd expect to find a simple lens. But what is a lens? What properties does it possess that makes it such a useful component in so many complex optical instruments? Let's start with light. These three laser beams demonstrate one very important property of light. Uninterrupted, they travel in straight lines. However, when they pass from one medium to another, they bend. This is called refraction. The amount by which they bend depends on the angle of incidence at the interface between the two materials. The greater the angle of incidence, the greater the refraction. Here, the block is geometrically simple, and it isn't too difficult to describe the behavior of the rays of light mathematically. I'm not going to do this, but you can see that with a rectangular block, the light is bent back to the original direction when it emerges. What happens with a different shape? Again, the light bends, but because it strikes the surfaces at different angles, it's bent still further as it emerges. So the total amount of bending depends on the shape of the object it passes through. This shape's a combination of a rectangular block and a pair of prisms. The middle beam strikes the rectangular block so that the angle of incidence is 0. The beam carries on undeflected. The outer beams pass through prisms and are bent away from their original direction. The important feature of this arrangement is that the rays converge at a point. Although the shape of this object is rather complicated, we are still dealing with straight surfaces, so we could easily calculate how these rays are deflected. Now I think you can see that the shape of this object is very crudely beginning to look like the more familiar converging lens shape. So we might reasonably expect that if we put a lens into the rays, it would behave in roughly the same sort of way. In the most accurate work, you'd have to deal with refraction at two curved surfaces. However, for most practical purposes, you can forget about the details of the refraction in the lens and simply regard the lens as a component that bends light in a particular way. The first thing about optics that any schoolboy learns is that he can set fire to a piece of paper using a lens. While he wouldn't think of the prank in terms of image formation, that's exactly what he's doing, forming an image of the sun on his piece of paper. The paper catches fire because the energy in the light from the sun, which falls over the area of the lens, is converged and focused by the lens into a spot. And that spot contains all the energy that was spread over a large surface. The concentration of energy produces enough heat to set light to the paper. Essentially, the object, in this case the sun, is so far away that the incident light rays are parallel as they enter the lens. They all focus at a point, the focal point. The trick will only work if the paper is at the correct distance from the lens, and that distance is called the focal length of the lens. Let's do this a bit more scientifically. This is an optical bench. Essentially, it's nothing more than a heavy iron bar that allows us to align the optical components. The object is an illuminated slide of a bunch of grapes. We can place the lens onto the bench and a screen. Now, for any position of the lens relative to the object, there's a unique position of the screen which will produce a sharp image. Now, it doesn't matter which way around the lens is. It's equivalent that way or that way. And the fact that we can cast the image onto a screen means that we call it a real image. Believe it or not, we now have all the information in our hands to set about laying down the rules by which we can predict not merely where an image will be produced by any lens, but what size that image will be in relationship to the object. If a ray travels parallel to the principal axis, marked PA, it will pass through the focal point, F. The converse is also true. If a ray is incident through the focal point F, then, after refraction, it will travel parallel to the principal axis, PA. Finally, if a ray is incident through the center of the lens, it passes on undeviated. So if we know the focal length of a lens, we know where the focal points are, and it's a simple matter to construct the position of the image of any object. For example, here's an axis. Think of it as an optical bench. Mark in the focal points and put an object in front of the lens. To construct the image, draw in turn, the three rays. First, a ray parallel to the axis. This is refracted through the focal point. Then a ray through the other focal point, and this is refracted parallel to the principal axis. Finally, a ray through the center of the lens, and this passes on undeviated. You'll see that after refraction, they all pass through the same point, and so this must mark the tip of the image I, and so we've located the position of the whole image. This is a very simple construction, but is this really what happens in practice? We've arranged the laser beams so that they follow these same paths, parallel to the principal axis, through the focal point, and through the center of the lens. As you can see, the result is exactly the same as the computer diagram. So it seems as if this simple construction works. Now, as you know from the earlier experiments with the optical bench, the position of the image changes as the position of the object changes. Let's see what happens to the image as an object moves closer to the lens. We can plot a graph of image distance V against object distance U. As the object gets closer to the lens, the image moves away, and at the same time gets bigger. When the object gets close to the focal point, the image moves away to very large distances indeed, and the graph shoots away. Let's stop the object before we reach the focal point. So far, we've said nothing at all about the size of the image. With the lens in this position, the object there, we have a diminished image on the screen. If, however, we move the lens towards the object, there comes a point where we get another sharp image, but this time it's magnified. So in some way, the magnification of the image depends on the distance between the lens and the object. Now we can use the ray diagram to work out whether or not the image is magnified. U is the distance of the object from the lens, and V is the distance of the image from the lens. If big H is the height of the object, and little h is the height of the image, then the linear magnification is the height of the image divided by the height of the object. That is, magnification equals little h divided by big H. But the two shaded triangles are similar triangles, so that little h over big H equals V over U. So an alternative measure of magnification is given by the ratio V over U. Hence the ratio of the image distance to the object distance is a measure of magnification. We can use the graph of V against U to derive the graph of magnification as a function of U, the object distance. Let's plot the ratio V over U as a measure of magnification. For any point on the V against U graph, we can calculate the ratio V over U and plot it on the lower set of axes. As the object distance approaches the focal length of the lens, the magnification, measured as V over U, becomes very large indeed. When the object is at a distance of 2f from the lens, the magnification is 1. Now you'll notice that we've been careful to keep the object outside the focal length, and with very good reason. When the object is at the focal point, none of the construction rays cross each other. In this case, we say that the image is at infinity. However, when the object lies within the focal length of the lens, we see a new phenomenon. After refraction, the rays diverge. That is, no matter how far they are continued, they never cross each other, so they can never produce a real image. However, let's project the refracted rays backwards. Now we find that these projected rays do cross at a point. In other words, the refracted rays behave as if they had all come from the same point. So we can place an imaginary image at the point of intersection of these projected rays. There's no way that this image can be formed on a screen, so it's usually referred to as a virtual image. Let's look at this through a lens. Outside the focal point, the image is real and inverted. As the object approaches, its magnification increases until at the focal point it becomes infinitely large. Once inside the focal point, the eye receives the refracted rays and the brain assumes that they must have come from something real. So although the image cannot be projected onto a screen, it can be seen. In order to distinguish real distances from virtual distances, that is, distances from the lens to some imaginary image, we introduce a minus sign. So if U is the object distance, then an imaginary image distance will be minus V. The reason for this is that we are measuring imaginary distances from the lens against the direction in which light is travelling. We can now add further information to our earlier graphs of V against U and V over U against U. When the object lies within the focal length, the V against U graph becomes like this. As before, we can deduce the ratio V over U, and when this is plotted on the axes, the graph appears like this. Note that in both cases, the graph is negative, because the image distance V is imaginary, and therefore negative on our sign convention. These two graphs provide us with a useful summary of the sort of information we need to start thinking about using lenses in optical instruments. For example, suppose we wanted to build a camera. What requirements would we demand of a lens, supposing that we used a single lens? Well, the first requirement is that we produce a real image, because this has to be formed on the film at the back of the camera. This means that any object must lie outside the focal length, or turned the other way around, it means that the focal length should be so short that no object is likely to fall within it. So we might typically choose a focal length of, let's say, between 30 and 60 centimeters, about 1 to 2 feet. But the second requirement is a camera of a reasonable size. We know that to focus on distant objects, the image must be formed at the focal length. So the distance between the lens and the film for a given format is set by whatever focal length we choose, and that determines the size of the camera. For special purposes, we may be willing to put up with such a large camera. The focal length of this one is 360 millimeters. But for most photography, it would be more convenient to choose a shorter focal length, say 80 millimeters, or better still, one of 50 millimeters. The third requirement is that you want to be able to take photographs of objects at different distances from the camera. But you know from the earlier optical bench experiments that for any value of object distance, there is a unique value of image distance if the lens is fixed. So that, for example, if it produces the image of an object at infinity, objects at other distances will be out of focus. In this position, I'm so far from the camera that essentially I'm at infinity. So if the camera produces a sharp image of me, it will be focused at infinity, and all objects at infinity will also be in focus. When I move very close to the camera, the picture's obviously well out of focus. To bring it back into focus, we need to move the lens. So the three main requirements are: first, a real image; second, a camera of reasonable size; and finally, a movable lens. So let's see how these three general principles are applied in a couple of commercial cameras. One of the simplest cameras ever produced was the box camera. It contains a single lens set so that images at 2 meters are in focus. Nothing else. Well, let's see what sort of pictures it takes. It produces quite a good image of objects 2 meters or more away. But anything closer is well out of focus. And with this camera, there's nothing you can do to make them sharp. The major refinement of a modern camera is it provides us with a movable lens. This means that we can take sharp photographs of objects that are any distance from it. In this application, we're not too worried about magnification. If need be, we can always enlarge from the negative. But sometimes, of course, magnification is important. Let's look at the graph of V over U as a function of U. This is essentially a plot of magnification against object distance. If the object lies at 2f, then the magnification is 1. If the object is in contact with the lens, the magnification is again 1. Strictly, it's -1. Now let's think about a magnifying glass. The aim is to produce a magnified image. Suppose we wanted a magnification of 3. From the graph, there are 2 positions of the object that would allow us to obtain this magnification. If we chose V over U equals +3, then the magnification would be 3 and the image would be real. If we chose V over U equals -3, the magnification would again be 3, but the image is now virtual. Which should we choose? Suppose I want to use a lens as a magnifying glass to read a newspaper. Well, ideally, I want to form an image about 25 centimeters in front of the eye, because that's the most comfortable reading distance. So if I use the real image, that's the position of the image, the lens will have to be beyond that, and the newspaper will have to be beyond that. Not the most comfortable reading position. The other disadvantage, of course, is that the image is inverted. Now, if I choose the virtual image, the image and the object are on the same side of the lens. And so it's now quite easy to get a magnified image and hold the newspaper at the same time. And the other bonus is, it's the right way up. When the distance between the lens and the object is very close to the focal length, then we can, in principle, obtain any magnification we like. For example, in this position, we have a sharp image of the grid. If I move the screen further away and refocus, the image is magnified even further. But of course, for practical systems, this sort of length is far too great. But more seriously, if we go to extremely high magnifications, we run into another problem: distortion. One way to decrease the length of the system is to introduce a second lens. If we leave the screen undisturbed and focus, we find that the magnification is increased. However, if we move the screen closer to the lens system, we find that we have the same magnification as before, but now the length of the system has decreased. With a single lens, we are of course limited in the size of the image by the focal length of the lens. So if I wanted to take a photograph of that bridge, I'd just use an ordinary standard lens. Of course, if I wanted a photograph of the detail on the bridge, I could simply blow up the picture I've just taken. That, of course, is limited by the amount of graininess on the negative. But far better if I could achieve some magnification inside the camera. And to do that, I need another lens. Of course, if I wanted to take a close-up of this flower, I'd need still another lens. In fact, if I wanted to accommodate the requirements of all photography, I'd need a whole box of lenses. How much better it would be if I could have a single lens with a variable focal length. This lens system will do just that. It consists of a converging lens, a diverging lens, and another converging lens. No matter where this converging lens is, it's always possible to find a position of the diverging lens so that the image will be magnified and real. And this is the basis of the zoom lens.